Okay, this mini lecture is going to look at phase changes and how we go from liquids to solids, solids to liquids, liquids to gases, gases to liquids, and how much heat is involved. We learned that in order to change an object's temperature, we needed to either remove heat from it or add heat to it. And that was the whole relationship between the specific heat of the material and the temperature and the mass. It told us how much heat it would take to change that object's temperature. Well, what if I'm trying to change that object's state of matter? What if I want to go from a solid like ice to water? Does it look different? Well, it turns out it does, and we're going to explore how that transition happens. Now, we know that it takes heat in order to go from a solid to a liquid, but we have to do a couple of things, right? We have to get it up to that melting point, and then we have to melt it all, and then once I have a whole bunch of liquid, if I keep heating it, now I'm in liquid phase, so I change the temperature, and how does that all look? All right, so we're gonna graph it first and talk through it, and then look at it mathematically. So let's imagine that we are looking at water, and on this axis we have temperature, and on this we have heat. Okay, so the amount of heat added. All right. Now, if we are looking at phases, we know there's very specific temperatures that are important, right? We have the 0 temperature mark. That's when we go from a liquid to a solid or from a solid to a liquid. And we have the 100-degree temperature mark. And I'm not going to worry so much about my scales right now. We're just going to kind of look at the shape. Okay, so we can imagine that we know that as we add heat, we get a change in temperature that's proportional to the heat. So we expect as a heat is added, my temperature will change in a linear fashion. So if I'm in the solid phase, I would expect that my graph would rise linearly as I increase the heat. I get an increase in the temperature. But then I get to 0 degrees and things start to happen. As I add heat, I'm changing from a solid ice to a liquid water. And I have to get all of that ice converted to water before I could start heating it. The energy, the heat added, is going into breaking those bonds apart, right? Like turning that solid into water. So we get this flattening of our behavior as the temperature doesn't change as more heat is added. So during this part, this is all solid. And I'm increasing the temperature of my solid. This part is a mix of liquid and solid. And again, I'm using 0 degrees to represent kind of water that we're familiar with, but it could be anything. Everything looks the same, it just has different temperatures. So this is between kind of liquid and solid, and all of the heat I'm adding is going into converting that solid into a liquid. So I'm not getting any change in temperature, but I am getting a change in state as that happens. And then once everything has been converted to a liquid, I can start increasing the temperature again. So during this phase, everything is between a liquid and a solid. So both, it's a mixture. I put little dots around. And now everything is a liquid, and I can start increasing the temperature again. So as I add heat here during this entire time, everything is a liquid. And I'm increasing the temperature. And then I get to 100 degrees for water, and things start to go into a gas. And so I'm now using the energy to go from a liquid to a gas. So here I'm in gas and liquid at this 100 degrees. I'm using all that energy, and then once everything is converted, I'll make it yellow here. So this is all liquid to gas, and once everything is converted, we have steam or water vapor. Okay, so now I can start to increase the temperature again. So during these phases where I'm in liquid solid or gas liquid, all of the energy that's being added to the system, the heat that's being added is being used to change the phase of my, in this case, water. Okay? So what influences that flat part? Well, like the specific heat, there's a property of the material. It's different for water than it is for any other, like carbon dioxide, than it is for other things. Okay, so everything has its own, what we call latent heats. So there is the amount of heat necessary during this phase is related to a property called the latent heat, where L is the latent heat. Now there's two of them. Okay, there's two we have to pay attention to. There's one for when we're going from a liquid to a solid. That is the latent heat of, oh my gosh, I just lost it, fusion. So we say it as LF, goodness grief. So that is the latent heat of fusion. And there's a different number that is when we are going from a gas to a liquid, and that is the latent heat of vaporization. Okay, and these are essentially, they're similar, okay? So it's essentially how much it takes to, I just want to get this right, to convert, how much heat it takes to convert 1 kilogram of the substance into, going from a solid to a liquid, is related to the latent heat of fusion, and how much heat is necessary to convert 1 kilogram of a substance from a gas into a liquid is the latent heat of vaporization. So the amount of heat I'm dealing with is not only going to depend on that, but how much stuff I have. If I have 3 kilograms of ice, it's going to take 3 times as much heat as it does for 1 kilogram of ice, right? The mass is going to be important. Okay, so the amount of heat to transfer phases depends on the mass, and then it depends on which of the two latent heats we are dealing with. This is the generic equation, so you got to know if you're going from a solid to a liquid or if you're going from a gas to a liquid, which of the two latent heat of fusion or latent heat of vaporization you use in your relationship, okay? All right, so let's do an example. Let me pull up that example while I erase the board and you can read it. So we're going to look at how much heat it takes to take some water, turn it into ice, and then cool it to negative 10 degrees. How much water does it take? Sorry, how much heat does it take to cool 10, or however much I have on that little note there, our water, turn it into ice, and then cool it? All right. If I was really sophisticated, I would fast forward automatically through all this. I'm not that sophisticated yet. I just want to get these videos out for those of you who are interested in this material. Okay. So what do we have? We have 10 kilograms of water, at 10 degrees, at 15 degrees. And I want to convert it to ice at minus 10 degrees. Okay. How much heat is going to be required? How much energy am I going to use? Now this is going to assume nothing is lost, okay? We are in an isolated system. All right, well, a couple things are going to be happening. What's going to happen first? Well, first I have to cool the water to the freezing point, to 0 degrees. So let's break down these steps. So step number 1, I have to cool the water to 0 degrees. That's the first step. Step number 2 is I have to convert the water to ice. That all happens at 0 degrees. And then step number 3 is I have to cool the ice to minus 10 degrees. All right? So we're going to convert the water to 0 degrees. Then we're going to convert the water to ice, cool the water, from 15 to 0, convert the water to ice, and then cool it from 0 to minus 10. So which of my relationships are going to be useful? Okay. The heat used, or taken or added, remember, if I'm within a phase, is related to the mass times the specific heat times the change in temperature that I'm obtaining. The heat, if I am within phase changes, is the mass times the latent heat, depending on which latent heat I'm using. And because I'm going from water to ice, I'm going to be using the latent heat of fusion. All right, so those are the things we want to keep in mind as we explore this problem. So the total heat that we're going to need is going to be, the total is going to be the heat to go from 15 degrees to 0 degrees, plus the heat for the phase change, plus the heat to go from 0 degrees to minus 10 degrees. Those are the three we need to work on. All right, so let's take them one at a time. Let's do this one first. We are in a constant phase, so I'm going to use the specific heat relationship. So I have how much heat is the mass of the water times the specific heat of that water times the change in temperature I'm interested in. So this is for 15 to 0. We're told the mass of our water is 15 grams. Nope, 10 grams. The mass of the water is 10 grams. 15 grams is what I have calculated. So we are going to change this number to 15. I'm just going to change that to 15. All right. Easy fix, easy fix. Because I don't have a calculator in front of me. All right, to recalculate it. So, mass of 15. The specific heat of water, liquid water, is 1486. And we are going from our final temperature of 0 minus our 15 degrees. Okay, so we're doing a change in temperature. We're just going to keep this positive to get the total amount of 15. So our total heat needed to do this part is 334,350 joules. Okay. So that's this part. So I'll put that in there. 350. All right, now we need the heat for the phase change. Well, that is going to be Q equals M times our latent heat of fusion for water. So again, we have a mass of 15. The latent heat of fusion for water is 3.33 times 10 to the 5th. And so the amount of energy we need to convert 15 grams of water into ice is 4,995. I had to find it in my notes. 000. So 4,995,000 joules. Lots of energy to convert relative than to change its temperature. So we'll add that up here. So I have 4.996 times 10 to the 1, 2, 3, 4, 5, 6. And then we need to know how much heat it's going to take us once everything is ice to go down by 10 more degrees. So that, again, is in a single phase. So we are going to use this relationship. And again, it's a 10-degree change. So we have 15 grams. Our specific heat of water is different than the specific heat of ice. So the specific heat of ice is 2100, okay, times our temperature change, in this case, of 10 degrees. And we find that our amount of heat needed to cool ice from 0 to minus 10 is 315,000 joules. So we will add that up here. And our total heat needed, if we add up all of the heat that needs to be removed, this is a subtraction, we need to remove that heat, we end up with 5.6 times 10 to the 6th joules. So, assuming all my math is right, we are, and now that we've changed it to 15 kilograms of water instead of 10, we just wanted to go through the process to recognize what we need to pay attention to, right? Recognizing that what happens while we're cooling or heating is different than what happens when we're changing phases, and so we have some different constants that we have to pay attention to. When we are doing a whole process, we have to consider the fact that we go through 3 different steps and analyze that appropriately for the given state that we're looking at. So we'll do another example in another video, brief introduction to the idea of using heat to change phases and latent heat. Good job.